Hello, everybody. Hello and welcome. This is Prague seminar for mathematical physics, and today with our kind guest Sylvain Lavau, with affiliation from Ruder Boškovic Institute. Sorry for little inaccuracy made in the announcement. And Sylvain brought a very nice topic for us. And more concretely speaking, it's a graded geometric perspective on tensor hierarchies. So Sylvain, we are pretty happy you accepted our invitation and you eventually arrived in spite of this inaccuracy. So thanks again, and
Yes.
our floor is yours.
Thank you very much. I'm very happy to talk in this seminar because I think the topic is really adapted to the audience. So this topic is a long-standing topic I have been studying in the past 10 years or so, on and off. And so we reached some understanding on the tensor hierarchies. And so I will present you kind of an overview of the topic, of what we know from the mathematical perspective, and what we can do about them in the future. And so the work is joint with Thomas Basile, based at the University of Mons in Belgium. So let me start with a bit of mathematics. So I'm positioned in mathematical physics, and my view about it is that I take inspiration from theoretical physics, and mathematical physics developed new mathematics in order to be in interactions with physics, but also the mathematics we develop in mathematical physics, they become autonomous, and they even go further in the field of mathematics. So it's as if we have physics here and maths here, but it's not even reality. We have discussion between the two fields, but also then we have also notions going through more deeper mathematics. And so from my experience about the tensor hierarchy is that physicists, they work from 4 or 3 to 11 dimensions. But from the mathematical perspective, there are too much details. They exhaust all the cases. And from the mathematical perspective, we need to abstract a bit from this to get some more mathematical grounding and find some good, interesting things to say. So about this notion of tensor hierarchy, it emerged in the 2000s, at the beginning of the 2000s, and since then it has been like investigated a lot in gauge supergravities, in exceptional field theory, and in theoretical physics, but from the mathematical perspective, not so much. So this is the aim of the talk, is to discuss about it. And we are at a point where we want to bring these notions of tensor hierarchy and graded and Poisson geometry together to find some interesting statement to say about them. If you have questions, do not hesitate. I don't have many slides, so we can discuss during the talk. So from my perspective about the topic, so I'm located in the mathematical physics realm, so I don't understand, or I don't study really much of the theoretical physics papers. From what I understood, at least, is that the notion of embedding tensor and tensor hierarchy had been introduced at the beginning of the 2000s as a way of gauging supergravities. And it inherits from the work of DeWitt and Nicolai in the 80s, at the beginning of the 80s, where they introduced this SO8 supergravity and the T-tensor. And so the first axiomatization of the tensor hierarchy has been done in the 2008 with 2 papers by DeWitt, Nicolai, and Leben, where they abstract what they found in from 2001. With co-author, because I didn't write all the people that work on this topic in the 2000s, but there are much more, obviously. And then this led to several more abstractization of the concept. So I want to emphasize the work of Jacob Palmqvist, who found the the first way of properly defining tensor hierarchy from Borcher's algebra. And this comes actually very funny because it comes from other observations made by Kremer, Julia, Liu, and Pope from earlier. So we have kind of both sides of the papers from the 80s and 70s merging in the 2010s. Also, I want to emphasize this paper, the tensor hierarchy simplified by Greitz, Ho, and Palmqvist, because in this paper, it's very important. They establish that the tensor hierarchy is a DGLA, it's a differential graded Lie algebra. And this was the beacon that guided all my research, and also that guided also the work of Home and Bonezzi in the late 2010s. And my work on the tensor hierarchy sits at I got this inspiration from the work of Santleben and Jakob Palmqvist to find a mathematical categorification of the tensor hierarchy from the realm of categories, functors, and find a way of properly define mathematically and construct this DGLA. Obviously, there are other people like Martin Sedervold that may collaborated with Palmqvist who did a good job regarding this topic. And what I want to emphasize today is that we are here. I mean, now we know how to build the tensor hierarchy. This is a DGLA that we know how to build it. And the work of Home and Bonezzi in 2020 and 2021 was kind of improving what was already done in 2014 by Palmqvist and collaborators by giving much more details. But there is not this graded geometric perspective on this. And so I want to incorporate the graded geometric perspective to actually, let's say, coin all the tensor hierarchy construction and data in a very compact way. And I also, additionally, we will probably add up this all N-infinity formulation of field theories inside, but that will be only at the end of the talk. I will present you how. Okay. And obviously, there are also work of, for example, the QP perspective of Arvanitakis, Osten. I didn't include them, but they will relate somehow at some point. So how do we build the tensor hierarchy? We start with the classical gauge theory, let's say. So you have the typical field strengths. The gauge parameter takes values in the adjoint representation. You have the field strength, the gauge transformation of the gauge field, and you have this Palatini identity. Now, so this is for young beats, for example. Now in supergravity, the gauge fields take values in the fundamental representation of the Lie algebra of symmetries, and this has some consequences because you need to couple the gauge fields to the other fields. So you need this embedding tensor, which is the map from the representation to the Lie algebra. And using this map, you can build this bilinear product on V. So obviously this bilinear product, so you use the embedding tensor and this representation of G on V. So this is on V, okay? And what is important is that the bilinear product we will see later, it's not a Lie bracket, it's a Leibniz bracket. But you have to use this bilinear product to define the field strengths, the gauge transformations, and then when you compute the gauge transformation of the field strengths, you observe that you don't have this identity because you have this part here. So you have an abstraction to the Palatini identity for the field strengths. And so you want to erase this term by adding a two-form fields. So you add another field, the two-form fields, and you need this to take value in another G module, W, and you need to bring this G module to the original representation defined by in which the gauge fields take values. Now that you have your two-form fields, you need to define a gauge transformation for these two-form fields, and then you also redefine the field strengths by adding this term. So all of these take values in V, and it's a two-form in V, and also the gauge variation of A, you need to add this term so that all the gauge transformation is consistent with the gauge transformation of B. And now, if you choose very well the gauge transformation of B to exactly compensate this term here, then you have the nice Palatini equation, meaning that the gauge field, the field strength, is transformed covariantly. But if you added a two-form field B, you need to add the three-form field strengths associated to it. And it implies, yeah, that you have that you need to check if it transforms covariantly or not, and you observe that it does not. So the problem now is that you need to add this a three-form field C, taking values in the module X, and you need a map from X to W to bring it, to redefine the three-form field strengths. Yes, H. And you do the recipe all over again. The three-form field H transforms covariantly, but the field strength associated to C does not, etc., etc., etc. So you end up with a tensor hierarchy, which is a chain complex of G modules related by a differential. So the P form takes values in these things, in these G modules. You don't have, there is no reason that the chain terminates, but since you are bounded by the dimension of space-time, you only care until the dimension of space-time. What is beyond, you don't really care. But algebraically, it has no hands. This chain complex here can be equipped with the DGLA. So this was the work of Panfist. This is very important, okay? But you observe that, so H is the image of the embedding tensor, but you may want, instead of H, you may want to include the Lie algebra G. But when you include the Lie algebra G, you need actually to go in the positive degrees to add more spaces so that the DGLA, which is only defined on the lower degrees, get defined on all the spaces. So you have two choices. Either you take this DGLA with H, or which is a proper DGLA, or you take the DGLA with G, but then you have all positive numbers. The problem is that the positive numbers, we don't really know what it's, the positive spaces, we don't really know what it is. In degree one, this is the G orbit of the embedding tensor. And then you have the nested commutators. I think it's probably related to the deformation of the embedding tensor, but we will not study them today, and this has to be investigated later. What we have to know is that actually we can only, depending on your choice, you can pick up H instead of G, and you have only the DGLA in non-positive numbers, but as you prefer. But what a good point is that if you take the bigger one, the big GLA, then you have this nice property that the differential is inner, meaning that actually the embedding tensor is the Hamiltonian function of the differential. Let's say like this, yes. And this homological property of the differential is nothing but the quadratic constraint. Nice. Okay, you have questions so far? No. Okay.
So, yes, we would have
yes.
one question probably.
How do you define this embedding theta, this capital theta?
Sorry, what?
What is it?
How is this theta defined? This embedding theta?
Yeah, how the theta is defined.
Yeah, probably. So that's the point. It's the next slide. So this theta is a map from a linear map from V to G, satisfying this constraint, the quadratic constraint. That's the only condition we ask for theta. So this we obtain a DGLA controlling the tensor hierarchy, and so the higher gauge, the gauge theory associated to this supergravity theories. So we know that if we are in if we have a higher Lie algebra, it means that the gauge algebra is not a Lie algebra. So we need to understand what is the gauge algebra at the core of this process. So this embedding tensor theta is just satisfies this quadratic constraint. So this I remind you that this product here is the action of the image of x on y. And so this quadratic constraint has two consequences. It implies that the image of theta is a Lie subalgebra of G, and that the V equipped with this product is a Leibniz algebra, meaning that we have a bilinear product. It is not skew-symmetric, but it satisfies the Jacobi identity, that it is a derivation of itself. So it's kind of a non-skew-symmetric analog of a Lie algebra. And so this is the gauge algebra. And you see that it is not Lie. So we have, in the gauge theory, we have a higher Lie algebra, we have a DGLA, that's why. And the slogan that we need to remember is that the embedding tensor is lifting the Lie bracket on G to a Leibniz product on V. And from this, we can construct, so the mathematical way of constructing the tensor hierarchy is the following. I mean, from the mathematical perspective, is that if you take this embedding tensor, then you also put at level 1 this the G orbit of the embedding tensor in this G module. Then you have to map the embedding tensor and also the representation of G on theta, because theta is lives in the G module, because theta lives here. And so we have a bracket between these two space, which is the action of G on V. We have a bracket between these two space, which is the action of G on R theta. And the action of between V and R theta is the embedding tensor, namely. And then what you do is that you take the free graded Lie algebra generated by V1 in degree -1, and you take the free graded Lie algebra generated by R theta in degree 1. So you have something that is naturally graded. And the second term is naturally isomorphic, for example, to the symmetric power of V, the second symmetric power of V. And then you use this bracket here to extend the action of R theta on the negative part using these linear constraints. So it means that when you use since theta, the embedding tensor, generates its orbits, you only need to define this bracket here between theta and an element of F2, F-2, which is the the symmetric power of V. And so basically you define it like this. This is called the linear constraint in supergravity, and it singles out a and from this you can just extend this bracket, the bracket between R theta and all the negative things by derivation and the Jacobi identity. And on the other side, actually, since this you can do the same on the other side, because actually these are just the commutators of morphism. For example, if you have a morphism here, and if you assume that chi is in the orbit, then you chi and psi also. So you can also define here using the same definition here. You can also define them like this. So you can use the compute their commutators and so on and so on. So it's very easy as well to define the commutator between V and the positive parts. So you end up with a differential graded Lie algebra defined over the two parts of the free graded Lie algebra on both sides. But then you factor out an ideal. And so you factor out the maximal peripheral ideal, which is the maximal graded ideal, which is concentrated in degree below -2 and above 2. So this ideal does not intersect V, G, or the R theta, the orbit of theta. And so this ideal is so that then the DGLA structure that we defined above descends to this space, graded space, which is the tensor hierarchy. And this tensor hierarchy has a very nice property, which is that if V is a Lie algebra, then all the negative space of degree lower or equal to -2 vanish. And if theta is G equivariant, then the R theta is the trivial representation of G, which is the meaning of G equivariance. And then all spaces of degree higher or equal to 2 vanish. So we have this by this procedure with this algorithm that from embedding tensor, you have a unique tensor hierarchy algebra with these properties. And a nice remark to notice is that the part of the chain complex that is below -2 is a direct consequence of the presence of a symmetric part in the Leibniz product. Because if you don't have a symmetric part, namely if you have a Lie algebra, then you don't have such spaces. So these spaces just can be seen as kind of a Liefication of the Leibniz product or of the embedding tensor. So as an example, we have two classes of example that are typical. When V is the Lie algebra G itself, that will be used for Chern-Simons and Yang-Mills theory. So V is the adjoint representation and theta is the identity. Then the tensor hierarchy is the following, because we don't have anything here because V is Lie algebra and the identity is G equivariant, so we don't have anything here as well. And this is the case for every differential cross module. On the other hand, if V is a general Leibniz algebra, we do not fix G yet, but then you take this particular subspace of V, which is the ideal of squares. So it's created from all the pairs of elements which are of the form like this, the symmetric product of yx and xy. Okay, sorry, it doesn't work well. And then you observe that this is an ideal with respect to the Leibniz product, and the quotient here is a Lie algebra. So you can find the embedding tensor is the projection. And so the tensor hierarchy associated to this case is the following. We have something in degree -2, which is the ideal of squares. And then we have the other typical elements. And this is whenever V is a semi-direct product, like in the work of Quignon and Weinstein, this is a typical example of this situation, or when we have an augmented Leibniz algebra. So you can see that using the tensor hierarchy, we will, if we can define Chern-Simons and Yang-Mills theory in this formalism, we can define also all the Leibniz gauge theories and even higher types, higher kinds of gauge theories, much more complicated, let's say. Okay, do you have questions? Sorry.
Yeah, we would have one question.
Yeah.
Of this quotient, which is highlighted, I mean, as it's not first glance, as doesn't seem to be a subset of subspace.
Can you translate it? I don't hear you well. Can you translate it?
Maybe if you can elaborate more on how this quotient works.
Which one? This one? Or this?
No, this G with subscript B, I guess.
Yeah. So you just you just take the. I mean, this is the quotient of the. Okay. Yeah. Right. Okay. So the Leibniz product. Wait. Yeah. Can be decomposed into two parts, which is the skew symmetric part and the symmetric one.
Mm-hmm.
And so if you remove the symmetric part of the, and also, so this is fact number one. Also fact number two, the Jacobiator of the skew symmetric part is something symmetric. That is important. So what you have is that if you remove if you factor out the symmetric part, then the skew symmetric part becomes a Lie bracket. So that's why this quotient becomes a Lie algebra. And and the action of this Lie algebra on V itself is the usual action. I mean, it's the action of V on itself, because I didn't say that as well. The ideal of S, it's in the center of the Leibniz product. So the action of V on V itself is the action of V on V itself. So we have a typical situation where we have an embedding tensor.
Mm-hmm.
Yeah.
Okay.
Okay. Yeah. So now let's incorporate the differential form. So if you have a n-dimensional smooth manifold and you want to incorporate the differential forms, you define a DGLA on this product. So what I will say so far, like, what I'm saying now is like it has been found already by it's not new. It has been written by Palmqvist, Bonezzi, and Holm. So, but I'm giving you a graded geometric perspective about it. So you define this DGLA, this bracket on the forms taking values in this tensor hierarchy. And you observe that from a typical graded geometric perspective, that this DGLA is the space of sections of this pullback vector bundle here, which is pulled back over the T1M. So what we have now, if you define the total degree as the form degree and the tensor hierarchy degree, you see that we have L is a graded vector bundle over T1M. Actually, we will see it is a DG vector bundle, and it will be in fact a DG Lie algebra. From this perspective of the degree, you see that the embedding tensor is a degree plus one section of L, because the embedding tensor was living in this space R theta, which has degree one, and it is constant, so it's degree one. And additionally, it is a Maurer-Cartan element of the DGLA because it satisfies the quadratic constraints. So what you want to do when you have a Maurer-Cartan element is to perform a gauge transformation of it. So what you do is you take a degree zero section, but you concentrate it in negative degree. So it is equivalent to having only one forms and so on. So one forms, two forms, and not functions. And this is nice because if you start with one forms and so on, so the one forms then take values in the space in degree -1, etc., etc. This action, the action of this term alpha of this degree zero section is nilpotent, so you can make a gauge transformation of the Morar-Cartan element without much caring about what is happening. And indeed, what you find is that when you perform this gauge transformation, you develop in terms of form degree. So here you have one form, two forms, three forms. What do you observe? You observe that you see the field strengths of the tensor hierarchy appear in the development. So what you do is that what it means is that when the field strengths of the tensor hierarchy are appear as a byproduct, as a gauge equivalence of the Morar-Cartan element theta. And so obviously this omega alpha here is also a Morar-Cartan element. And when you write the Morar-Cartan equation for this omega alpha and you develop it into form degrees, you observe that you have the Bianchi identities of the tensor hierarchy, which are not trivial identities. I remember, for example, the first one is that the covariant derivative of the first curvature is the image by this differential of the second curvature, and so on. So you have the Bianchi identities, and also since it is a Morar-Cartan element, you can twist the differential on this DGLA. So you twist the Durham differential by adding this inner term. And so you observe that this is a degree +1. First of all, it is a differential, and it is compatible with the graded Lie bracket. So what it tells you that this thing is, first of all, a Lie algebroid, graded Lie algebroid, but also you have a compatible differential, which turns it into a DG Lie algebroid with 0 anchor, of which the degree 0 sections with positive form degree are the gauge fields, and the degree -1 sections are the gauge parameters. So the visual perspective on this is the following. On the horizontal axis, you have the tensor hierarchy degree. On the vertical axis, you have the form degree. Then this is alpha, a gauge field. So you see that it starts in tensor hierarchy degree -1 because we want to start with a 1 form. So this is a degree 0. This is total degree -1. This is total degree +1. And so the blue line represents the Morar-Cartan element omega alpha after we gauged transform theta, the embedding tensor, which is here. And at the field strength then lives at each point here. And in orange, I represented the differential S alpha, which is the twisted differential, the Durham differential twisted by omega alpha. And so what you can see is that at S alpha send thing of total degree -1 by two things of total degree 0, and this term of total degree 0 is sent to this term of total degree +1. So you see that we have a complex which is diagonal, which is reminiscent of what happens in BRST. And also, actually, you don't really need to care about what happened here, because what I told you is that if you want to only check H, to only put H in degree 0 instead of G, you only have the non-positive part of the tensor hierarchy. So what you really care is actually what happens on the left here. Right, and also I want to mention that it is reminiscent of the work, that we will address just in a few minutes about the L infinity formulation of field theory, because we have something in degree -1. The gauge parameters in degree -1 are sent to the things in degree 0, the gauge fields, which are sent to the equations of motions in degree +1, etc. So I think we have like kind of in this representation, we have kind of a lot of informations that describes the tensor hierarchy. I will just comment about the gauge transformation. So you see, you pick up an element of total degree -1, starting in with functions valued. Yeah, we start with function valued in V, and then a one form valued in W, and external two form valued in the thing in X. And so the way we define the gauge transformation of alpha is by this very elegant formula. The problem is that it does not define the proper gauge transformation. It defines what the physicists call the covariant gauge transformations, which are obtained from the traditional gauge transformation through like an exponentiation procedure. The point with this covariant gauge transformation is that if I understood well, the algebra of traditional gauge transformation, so with the small delta, is closed. This was in the papers in 2008 by DeWitt, Nicolai, and Sentleben. But the algebra of with the big delta is not. But the big delta allows to very quickly and facilitate the computation of showing that the field strengths transform covariantly. So there are still some things to understand and dig in this direction. Do you have questions? Because I will conclude in the 5 next minutes.
It doesn't seems to be the case right now.
Okay. And so in the forthcoming future, we want to connect all this formalism with the L infinity formalism introduced by Hom and Zwibar at the end of 2010s. What we know for sure is that from a DGLA, we can always define a L infinity 1 algebra on the negative part. The problem with this L infinity 1 algebra, it's very uninteresting because all even brackets are vanishing except L2. So it is not the L infinity algebra that encodes the tensor hierarchy, because the field strengths in the tensor hierarchy, they have components for every even terms. So what we can at least say is that if you modify the gauge field alpha by doing this Baker-Campbell-Hausdorff exponentiation, then you redefine it and you obtain a new field alpha prime. And then if you rewrite the field strengths in terms of alpha prime, so instead of C, you have C prime here, you observe you can write the first field strengths of the tensor hierarchy under this form, which is typical of the L infinity formulation of field theory. So what we know, so it means at least that we have an example. I mean, theoretical physics tells us that there is a L infinity algebra hidden behind the tensor hierarchy. This is for sure. It is not the Getzler L infinity algebra, because this L infinity algebra has 4 brackets, 5, 6 brackets, all even brackets exist. So we conjecture that we have an interesting L infinity 1 algebra structure on the negative part of this DGLA, but we don't have the proof, a mathematical proof of the existence yet. If you heard about it, let me know. That would be a very good point and helpful. But so we know this is a possibility, and so in the following we assume this L infinity algebra exists. At least we have this one of Getzler, but it's not very interesting. If you assume it exists, and if you define an inner product on the negative part of the tensor hierarchy, then this inner product depends on the space-time dimension, because you want to couple the forms in V with the forms in the highest, the lowest space of degree minus n. And so that would probably turn this gradient manifold into a symplectic n+1 gradient manifold. Additionally, with the L infinity algebra perspective on field theory, we can define this all the Chern-Simons type topological theories, and then the equations of motions, as I said earlier, there would be F, the field strength, and the compatibility between the Q structure, so the L infinity algebra that we have, and the P structure given by the inner product would allow us certainly to use the KSZ, which probably would give us maybe this action. This is conjectural. We are not yet here. And eventually we can always define Yang-Mills type theory by, if you need this, you need some duality between space of degree P and n-2p, n-2 minus P, together with a Hodge star at the level of forms. And so I want to summarize my presentation by saying that what we saw is the following. We start with an embedding tensor. And from this embedding tensor, we have an explicit algorithm to build the tensor hierarchy. And from this, by incorporating some graded geometric content, we can actually have a very compact way of defining topological and non-topological field theories associated to the tensor hierarchy. And this field theory, they include Chern-Simons and Yang-Mills, because we can reformulate Chern-Simons and Yang-Mills in terms of tensor hierarchy, but also all the Leibniz type gauge theories and other kinds of whatever exists, I think, in a simplified version of the algebras that we see in supergravity and exceptional field theory. Thank you.
Thank you very much for the inspirative talk. And now I'm opening the discussion panel. So if you have any question, please ask.
A question regarding this embedding tensor. So is it clear that it exists, first of all?
Is it clear that
Good question. Not clear. No, because you need to satisfy the quadratic constraints. So no.
But it does.
But so it's probably the solution of a cohomological. It's probably a cocycle or something in some cohomology. Usually in physics, what they do is that they take instead of, since they don't assume the embedding tensor exists, they take the whole space of morphism from V to G, and then they pick up since they work in precise examples, they can check, do we have an embedding tensor inside this space? So.
Okay. And if it exists, is it unique? I mean, and if it's not unique, then is the GLA differ?
So what do you mean by unique or not unique?
Like up to scaling, or up to some trivial modification? Up to kind of homotopy, or
So do you mean by this? Do you mean
it probably means it defines the same cohomology?
Right. So, but by unique, do you mean that because we can have two embedding tensors different, and they probably don't define the same cohomology, because the cohomology is, from what I understood, is the massless bosons, and I wouldn't go further than that because I'm not a specialist about the topic, but if you change the embedding tensor, usually you change the space even of the higher spaces.
Okay.
Because the higher spaces are defined by the Leibniz product, the symmetric part of the Leibniz product. And so if you change the embedding tensor, you change the Leibniz product, so you change the symmetric part, so you change the higher spaces.
Okay, thank you.
Thanks. There is another question from the chat, and it's question: is M compact because of the scalar product identification?
Oh yeah, we are not until we are not at this point yet. We didn't work on the scalar product yet, but the scalar product is in the fiber. So I don't think we need M compact. It's only in the fiber. I mean, in the tensor hierarchy.
Okay, thanks.
It's like a generalization of the quadratic Lie algebra, but instead we have it's on the DGLA and.
Yeah. Okay, fine. Any other question? Yeah, there's some additional comments in the chat. Fiber is infinite dimensional.
No, so the fibers is each degree is finite dimensional, but it can be infinite on both sides. This is what I think we can call finite type graded vector bundle. But even usually, as I said, if you have the base manifold which is of the dimension n, you can stop at, you can only take the things that are, you can stop at degree minus n, because if I'm not mistaken, so you can, I think you can end up with some finite graded vector bundles both on the left and on the right if you pick up the Lie algebra, the sub Lie algebra H instead of G.
Yeah, one can take direct sums actually.
Yeah, so I didn't comment about the positive part because this is not so well known. So instead of having G and the positive part, we can take H, and then the DGLA stops at level 0.
Yeah.
Sylvain, may I ask you some formulas in Grove for the this two-form fields, three-form fields, and then the H transformations? They are kind of reminiscent to potentials in higher H theory, like potential, like for church or you know, two group bundles with cross module structure.
Which kind of formula in what?
You know, you had the differentials and the gauge transformations for A and for B, and then maybe you have some C.
Okay, so I'm sorry, I didn't understand the question.
Okay, so maybe the question was confused.
It concerns the potentials.
Yeah.
But for cases of higher gauge.
Yeah.
Like in case when you consider bundle terms.
Yeah.
Oh wow.
Even in the beginning.
In the beginning.
If you use, I don't know much about bundle jobs, but if you use like something that looks like a Lie algebra cross module, is it related to this?
Well, that's my question somehow.
Because a Lie algebra cross module generates here it generates a Lie algebra cross module is a tensor hierarchy.
Yes.
So yeah, as soon as you have a Lie algebra cross module, this is the tensor hierarchy associated to it.
Mm-hmm.
Okay.
Yeah. And actually, this was a big inspiration for my paper with Stashev, and also the addition that we made with Panfist, is that the Lie algebra cross modules, they have they can be reformulated in terms of a DGLA. So, yeah. And this DGLA is precisely the DGLA of the tensor hierarchy, associated with this differential cross module.
Okay.
So the differential cross module is really an archetype of an embedding tensor, and the tensor the DGLA formulation of the Lie algebra cross module is the tensor hierarchy of the differential cross module.
Mm-hmm.
Okay, thank you.
Okay, any question? Maybe I would have one meta question. I pretty much resemble from your description something around a construction of Deligne groupoid associated to some gauge algebra. Can you see some interconnection between these? Because once you have a gauge algebra, you can construct more Cartan elements and make a homotopic quotient to obtain something like Deligne groupoid or even higher groupoid.
Okay.
And the question is whether this datum somehow relates to constructions you exposed, because I have a feeling this can be reconstructed out of this by some Lie differentiation or so. But it was just a meta question because
no, it's good.
I don't graph of Deligne groupoids and higher groupoids. So
I didn't know about this construction, but I will have a look. Thank you.
It's from paper by Manetti and Roger Bandiera, or I hope.
Okay.
Name is correct.
Okay.
And also Erza Gessler had
okay. The big team. Classico.
Yeah. Okay. So personally, I have no other immediate question right now. So thank you again for your nice replies.
Thank you.
And maybe further questions I will postpone to private mail conversations or something like
that. Yeah. That's good.
Thank you very much for coming, and nice topic you brought for us.
Thank you very much. Have a good day. Thank you for inviting me.
Bye-bye.
Bye.
Bye. Thank you.
Bye-bye. Thank you.